Hello my friends and welcome back to Sky Creative. Today we're taking you on a journey through some of the most advanced machining methods being used by major corporations worldwide. So grab your coffee, settle in, and let's discover. Let's start our journey with something that's been at the heart of every engine since the dawn of the automotive age, the crankshaft. Now, if you've ever wondered how these incredibly precise components are made today, you're in for a treat. What we're witnessing here is the Heller Group's revolutionary internal milling technology working on an HDI-6 crankshaft. The Heller Group, a German engineering powerhouse that's been perfecting machining technology since 1894, has developed this sophisticated system that would have seemed like science fiction to the mechanics of yesteryear. NTHE magic happens through what's called internal milling, a process where specialized cutting tools work from the inside of the crankshaft journals. Think of it like performing surgery from the inside out. The machine you're seeing can position cutting tools with an accuracy of just a few thousandths of an inch, something that would have taken master craftsmen hours to achieve by hand in the early days of engine manufacturing. NTHE crankshaft blank enters the machine as a rough forging, weighing several hundred pounds. The Heller system uses multiple spindles working simultaneously. Some machines feature up to 20 different cutting positions. Each spindle can rotate at speeds up to 8,000 RPM, while the crankshaft itself rotates on a separate axis. This dual rotation system allows for incredibly complex geometries to be machined with surgical precision. What's particularly fascinating is the coolant system. You'll notice streams of cutting fluid constantly bathing the work area. This isn't just for cooling. It's a precisely engineered mixture that removes metal chips, reduces friction, and maintains the exact temperature needed for optimal cutting conditions. The entire process is monitored by sensors that can detect vibrations as small as a human hair's width. NTHE tolerances we're talking about here are mind-boggling. The bearing journals must be perfectly round within 0.0002 inches. That's about 1/10 the thickness of a sheet of paper. The surface finish is so smooth it feels like polished glass, achieving roughness values that ensure the engine will run smoothly for hundreds of thousands of miles. Now let's travel to Dearborn, Michigan, where Severstal operates one of North America's most advanced steel mills. This facility represents the evolution of an industry that built America, using technology that would astound the steel barons of the early 1900s. And our journey begins in the blast furnace area, where iron ore, the same basic material used for centuries, undergoes a transformation that's both ancient and ultra-modern. The ore, typically sourced from mines in Minnesota and Canada, is mixed with coke and limestone in precise proportions. What's remarkable is how computer systems now control what steelworkers once judged by eye and experience. NTHE blast furnace operates at temperatures reaching 3,000 degrees Fahrenheit, hot enough to melt copper. Modern furnaces like Severstal's can process over 6,000 tons of raw materials daily, producing molten iron with a consistency that would have been impossible to achieve in the steel mills our grandfathers knew. From here, the molten iron moves to the basic oxygen furnace, or BOF. This is where the real alchemy happens. Pure oxygen is blown through the molten iron at supersonic speeds, burning away impurities and transforming iron into steel. The entire process takes just 40 minutes, compared to hours in the old open-hearth furnaces that once dominated American steel production. NTHE casting process that follows is a marvel of engineering. The molten steel, now at precisely 900 degrees, flows into continuous casting machines that shape it into slabs while it's still glowing orange hot. These slabs, some weighing up to 25 tons, move through the mill on computer-controlled roller tables that extend for nearly a mile. NTHE hot rolling mills apply tremendous pressure, up to 10,000 tons, to reduce these thick slabs into sheets, thin enough for automotive applications. What's fascinating is how the steel is reheated multiple times during this process, each time emerging thinner and stronger. NTHE cold rolling process that follows uses work rolls smaller than your steering wheel to achieve the final thickness and surface quality. The precision here is extraordinary. Thickness variations are controlled to within 0.001 inches across the entire width of the sheet. And finally, specialized treatments like galvanizing coat the steel with zinc to prevent rust, using processes that combine the basic chemistry discovered over a century ago with computer-controlled precision that ensures every square inch receives exactly the right coating thickness. Let's shift gears to Denmark, where Aros Hydraulic has been perfecting the art of hydraulic component manufacturing since 1977. Hydraulics, the science of using fluid power, has been around since ancient times, but what we're seeing here represents the cutting edge of this time-tested technology. Aros specializes in hydraulic cylinders and aggregates that power everything from construction equipment to wind turbines. What makes their approach special is the attention to detail that ensures these components can operate flawlessly for decades under extreme conditions. NTHE process begins with precision machined steel tubes that undergo a specialized honing process. This isn't just smoothing, it's creating a surface finish so precise that a hydraulic seal can maintain pressure for years without leaking. The honing heads use diamond abrasives and operate with tolerances measured in micrometers. That's smaller than bacteria. NTHE piston rods you see being manufactured require a different approach entirely. These components often need to withstand forces equivalent to holding up a loaded freight car while moving smoothly enough for precise positioning. The surface treatment involves induction hardening, where electromagnetic fields heat just the outer surface to temperatures over 800 degrees Fahrenheit, creating a wear-resistant layer while keeping the core tough and resilient. What's particularly impressive is the assembly process. Each cylinder must be tested under pressures that exceed their working conditions by significant margins. The test equipment can generate pressures up to 10,000 psi, enough to cut through steel if misdirected. Computer-controlled test systems monitor for even the tiniest pressure drops that might indicate a future failure. NTHE quality control processes here would impress aerospace engineers. Every component is tracked through manufacturing with serial numbers and documentation that follows it throughout its service life. This level of traceability ensures that if a component performs exceptionally well in the field, the exact manufacturing conditions can be replicated. In FOR wind turbine applications, these hydraulic systems must operate reliably in conditions ranging from Arctic cold to desert heat, sometimes for decades without maintenance. The specialized seals and fluids used in these applications represent materials science advances that have revolutionized industrial reliability. Moving into the world of infrastructure, we encounter Apilion's automatic concrete pipe cage welding machine, a perfect example of how automation is revolutionizing even the most fundamental construction processes. Concrete pipes have been the backbone of municipal infrastructure for over a century, but the reinforcement cages inside them were traditionally assembled by hand, a labor-intensive process that required skilled welders working in challenging conditions. This automated system changes everything. The machine feeds steel wire from multiple spools simultaneously, positioning each wire with millimeter precision while creating perfect spiral patterns that provide optimal strength distribution. The welding process uses precisely controlled electrical resistance to fuse the intersections, creating joints that are often stronger than the base material. What makes this particularly impressive is the automatic cage removal robot. Once welding is complete, robotic arms grip the finished cage and lift it clear of the work area with movements that are both powerful and surprisingly gentle. The entire process, from wire feeding to finished cage delivery, takes just minutes compared to hours of manual labor. NTHE consistency, achieved by this automated process, ensures that every concrete pipe will have exactly the structural properties the engineers specified, eliminating the variability that was inevitable with hand assembly. Now let's explore thread rolling, a manufacturing process that transforms how threaded components are made. The Tesker Model 740 represents the pinnacle of thread rolling technology, capable of applying 340,000 pounds of rolling force to create threads that are actually stronger than cut threads. And traditional thread cutting removes material, weakening the part. Thread rolling, by contrast, displaces and compresses the material, creating threads with enhanced fatigue resistance and superior strength characteristics. It's a process that harnesses the natural properties of steel to create better products. What we're seeing here is the production of a 4.5-inch diameter Acme thread, the type used in heavy-duty applications like machine tool lead screws and industrial lifting equipment. The 1.5 threads per inch specification means each thread must be cut to extraordinary precision to ensure smooth operation under load. NTHE rolling dies themselves are works of art, precision machined from tool steel and hardened to withstand the enormous forces involved. These dies essentially flow the steel into the thread form, creating a surface finish and strength that cutting simply cannot match. NTHE 340,000 pounds of force applied during rolling is distributed across the entire thread engagement area, but the pressure at any single point can exceed 200,000 psi. The machinery required to generate and control these forces represents some of the most robust engineering in manufacturing. NTHE CDS, cold-drawn steel material being processed here, has been specially prepared for thread rolling. The steel's grain structure flows with the thread form after rolling, creating a component that can handle the demanding loads these threads typically encounter in industrial applications. Quality control for thread rolling involves specialized gauges that check both the major and minor diameters, thread pitch, and lead accuracy. The tolerances achieved often exceed those of machined threads while providing superior mechanical properties. Here's where precision meets artistry. Sandvik Coromant, the Swedish cutting tool giant, demonstrates their advanced CNC milling capabilities by creating RoboBob, a robot head destined for exhibition at Stockholm's Technical Museum. This project showcases how modern CNC technology can handle both functional engineering and artistic expression. The complex geometries being machined here would have been impossible to create with conventional methods, requiring the 5-axis capabilities that represent the current state-of-the-art in machining. NTHE cutting tools being used are marvels of materials science, carbide inserts with specialized coatings that allow cutting speeds that would destroy conventional tools. The spindle speeds reach 12,000 RPM while maintaining positioning accuracy measured in thousands of inches. What's particularly impressive is how the CAM software plans every tool movement to optimize both surface finish and machining time. The tool paths you're seeing were calculated to minimize vibration, reduce tool wear, and achieve the complex surface textures that give RoboBob its distinctive appearance. This type of precision machining represents the democratization of manufacturing capabilities that once required teams of skilled craftsmen working for weeks to achieve by hand. Our final stop takes us through the complete steel pipe manufacturing process at International Pipe Industry Company, where raw steel coils are transformed into the pipelines that carry everything from oil and gas to water and steam across continents. NTHE process begins with massive steel coils, some weighing over 25 tons and containing enough steel to stretch for miles when unwound. These coils arrive from steel mills like Severstal, already processed to precise specifications for strength, chemistry, and surface quality. NTHE first step is uncoiling and flattening, a process that uses hydraulic systems generating tremendous pressure to remove the coil set or curvature that develops when steel is wound for shipping. Precision is critical here because any variation in flatness will show up as imperfections in the finished pipe. Edge preparation follows, where the steel strip edges are machined to exact angles that will ensure perfect welding. The cutting equipment uses plasma torches operating at temperatures over 40,000 degrees Fahrenheit, nearly 4 times hotter than the surface of the sun. Computer-controlled systems guide these torches with precision that keeps the cut edge straight within 0.020 inches over the entire length. NTHE forming process is where the flat steel transforms into pipe. Multiple forming stations progressively bend the steel using rollers that apply carefully calculated pressure. Each station bends the steel a specific amount, gradually creating the circular cross-section without overstressing the material. The final forming station brings the edges together with precision that allows for consistent welding. Welding represents one of the most critical steps in pipe manufacturing. The systems used here employ both inside and outside welding heads working simultaneously. The outside weld provides strength, while the inside weld ensures complete penetration and creates the smooth internal surface essential for fluid flow. Welding parameters, current, voltage, travel speed, and wire feed rate are controlled to tolerances that ensure every inch of weld meets stringent quality standards. NTHE heat treatment process that follows relieves welding stresses and normalizes the steel structure around the weld zone. Induction heating systems precisely control temperature across the entire circumference, ensuring uniform material properties that prevent failure points. End sizing and shaping operations use expanding mandrels that push outward against the pipe walls, ensuring perfect roundness and exact diameter control. The forces involved are enormous. Some sizing operations apply over 1,000 tons of force distributed around the pipe circumference. Quality control throughout this process would impress aerospace engineers. Ultrasonic testing systems scan every inch of weld, detecting flaws smaller than a pinhead. X-ray systems provide detailed images of weld quality, while pressure testing subjects each pipe to stresses well beyond its intended service conditions. NTHE final coating and marking operations prepare pipes for decades of service in challenging environments. Protective coatings applied using electrostatic spray systems ensure uniform coverage, while laser marking systems create permanent identification that will remain legible throughout the pipe's service life.